So now it is my pleasure to introduce the next speaker, Dr. Arik Bergman. Arik received his PhD from Tel Aviv University from the group of Moshe Tur, who's also here in the audience. And he spent between 2016 and 2020 a postdoc stay with my own group at Bar-Ilan University in Israel. And since 2018, he's also co-affiliated with the City University of New York, the group of Andrea Alu. And Arik will talk about non-Hermitian physics and exceptional point singularities based on Brillouin scattering. Arik, please share the screen and you can start at your convenience.
Yes, thank you, Mr. Chairman. Okay. Can you see my screen now? Okay. Yeah, just thumbs up. You hear me well? The screen is okay? Great. Okay. So, of course, first I want to thank the organizers for the invitation and the opportunity to present my research. I also want to say that it is unfortunate that we have to settle for an online meeting, but I guess that weak interaction is better than no interaction, which also applies to many of the systems discussed during this workshop. Specifically in this presentation, our everyman's optical waveguides are going to be standard single mode telecom fibers. And in order to avoid the scrutiny regarding the exceptionalness of the physics I'm going to discuss, some might find the title a bit pretentious, I'm going to put quotation marks right here around the word exceptional. And it will become clear in a few slides why I choose to call it that. Nonetheless, I do hope to live up to the high expectations set up by the previous speakers. So during this workshop, we saw many interesting presentations on classical optomechanics and quantum optomechanics, as did this puzzled wombat, presumably the one we saw on the previous slide, chewing the optical cable. And he is asking all sorts of questions, which wombats typically ask. One of them, naturally, is what this presentation is all about. So now we can make his life much easier by acknowledging that there is a closed list of types of photonic papers out there, of which he can choose. So to guide your eye, I encircled 2 of them, but several others may also be suitable. So in this work, we are going to use the tools from quantum physics, but we'll settle for a demonstration in a purely classical regime. And we are going to emulate a complex physical phenomenon, though not necessarily a solid state one, with optics, for the reasons that I will shortly explain. So speaking of animals and quantum mechanics, what in your opinion do the Schrödinger cat state of a quantum particle and the Fresnel diffraction of light have in common? Well, this is no brainer for this forum. They are both solutions of 2 isomorphic equations, the Schrödinger equation and the paraxial Helmholtz equation. What this implies is that the propagation of light in space is governed by the same equation as the evolution of the wave function of a quantum particle in time, subject to the approximations of the model. So here we identify that the refractive index plays the role of an effective potential in the optical wave equation. We will use this analogy very extensively from now on. Remarkably, similar analogy can be observed in the paraxial acoustic wave equation as well. The highlight of these results is that this effective potential of optical or acoustic waves can be spatially distributed arbitrarily. They can take any sign or even be complex. They can be time dependent or axial dependent in our case. And finally, we can use these principles to emulate artificial gauges that do not necessarily exist in nature. So interestingly, these effective potentials can be realized not only through material or structural modifications, but also dynamically controlled through interactions. So let's take a look at a few specific and more relevant examples. For instance, interaction with acoustic phonons can be used for dynamic control of the effective potential for photons, namely for amplification or depletion and phase retardation or advancement of a chosen set of spectral or spatial optical modes. I think that what stands behind these words is best captured in the following phasor diagram from Yosef's paper from a couple of years ago. It describes the equivalent nonlinear coefficient that governs the evolution of two optical probe waves. One is redshifted relative to the pumps, and the other one is blue shifted, denoted here by Stokes and anti-Stokes sidebands. The optomechanical nonlinearity is created by two strong pumps through forward stimulated Brillouin scattering. The two pumps are assumed to be undepleted, which effectively linearizes the potential. In fact, if not stated otherwise, for the rest of the talk, we will limit the discussion to the linearized forms of the governing nonlinear equations. What this diagram shows is that by controlling the detuning between the pumps, denoted here by the capital delta, the real and imaginary parts of the nonlinear coefficient can be flexibly modified. Generally, Brillouin waveguides offer a variety of means of coherent control of traveling photons, which can also be used for coupling between optical modes, form time-variant potentials, and so on and so forth. Well, photons and phonons can also switch roles. In this example, which was already discussed during the hot topic session, modulated out-of-plane illumination was used to induce a time-varying force through a radiation pressure. This time-varying force introduced coupling between adjacent nanobeams with different vibrational frequencies, marked here by the different colors. Authors of this paper suggested that due to the non-reciprocal phase shift that accompanies the optomechanical coupling, they can use it as a building block to assemble such a honeycomb lattice in which the phonon transport is governed by a synthetic magnetic field. Lastly, I want to bring your attention to a recent publication where they show the design of mode multiplexer in silicon for both guided optical and acoustic waves. In my opinion, such a platform can potentially support future studies of mixed photonic and phononic states in planar geometries with more complex interactions. To conclude the slide, I hope I convinced you that if you want, for example, to use topological principles to control the propagation of light or sound or both, or impose certain symmetries, you can use it optomechanical interactions to your advantage. In this work, we use the principles which just described to demonstrate the principle of PT symmetry in a standard optical fiber. The term PT symmetry was coined by Carl Bender in his seminal paper from some 20 years ago, where he postulated that one of the central results of the non-Hermitian theory is that some Hamiltonians, despite being non-Hermitian, may still possess a real spectrum if they obey PT symmetry. The Hamiltonian is called PT symmetric if it is invariant under the combined action of the parity inversion and time reversal operators. Commuting with the PT operator is a necessary condition, but it is not sufficient to ensure a real spectrum. Real spectrum is obtained only when the PT phase is exact. Otherwise, the eigenvalue spectrum is imaginary, and the state of a system is referred to as broken PT phase. The phase transition occurs at a singularity known as the exceptional point, where both the eigenvalues and the eigenvectors coalesce and become degenerate. Some of the most interesting consequences of PT symmetry and exception point singularities in linear or linearized systems are one, for example, is the asymmetry in the Riemann surfaces around the exceptional point, which can be used for asymmetric mode switching when executing an adiabatic loop around the exceptional point in the parameter space of the system. And another one is that the enhanced response to small perturbations near the exceptional point. Here you see an example of a resonator with two degenerate modes. One system is Hermitian, marked here in blue, and another one is non-Hermitian, marked here in red. If we introduce coupling between the two modes, the resonance splitting will show a square root dependence in the non-Hermitian case and linear dependence in the Hermitian case. Higher order exceptional points show even larger sensitivity and more involved topological features. In this work, we will show a realization of a two-level system, but the size of the system can be increased using the same principles. While Carl Bender claims that PT symmetry is a fundamentally correct symmetry of nature, which probably explains why I observed the PT transition in my backyard. By the way, is this also the reason why it is called the branch point? Anyway, for many years, physicists struggled to find a physical system that obeys this symmetry. Until some years later, it was noticed that it can be realized using complex optical potentials. To put it in simple words, the real part of the refractive index should be an even function of the spatial coordinate, and the imaginary part, which is gain or loss, should be odd. In fact, these results are platform agnostic. As we already saw above, such symmetry can also be imposed on an acoustic system by controlling the mechanical dispersion or dissipation. There have been many beautiful demonstrations of these principles and their applications in optics and photonics over the recent years, starting from a first demonstration of PT symmetry in coupled waveguides with differential gain in 2010. In this science paper, they showed that by adding absorption to one of the coupled microresonators, Raman lasing can be suppressed or revived as they tune the parameters of the system near the exceptional point. Another demonstration of enhanced sensitivity at a third order exceptional point in a coupled cavity arrangement with a carefully tailored gain-loss distribution. And in this recent example, also published in Nature, they demonstrated an enhanced Sagnac effect in coupled Brillouin lasers tuned to the exceptional point. However, common to almost all examples in this thriving field of research is that they employ nanofabrication techniques and require tight tolerance control of the resonance frequencies, gain, loss, or coupling in order to establish PT symmetry and reach the exceptional point condition. In my view, beyond the basic interest of this work of observing such dynamics in a simple system, such as the optical fiber, the fact that most practical systems are non-conserving suggests that they will be more properly treated in the frameworks of non-Hermitian physics. This will not suddenly turn loss into a desired feature, but rather offer unique handles on the problems involved in the propagation of coupled optical modes when dealing with imperfections or uncertainties that naturally arise in our systems. So in order to demonstrate PT symmetry in a standard single mode optical fiber, we employed a scheme known as Brillouin-enhanced four-way mixing. Our degrees of freedom were two continuous wave probe tones, A1 and A2, separated by the frequency delta N. They were amplified and dissipatively coupled by a pair of counter-propagating Brillouin pump tones, marked here in blue, separated by the same frequency delta N. Maximum gain in coupling is achieved when the pump probe separation is tuned to the Brillouin frequency shift of the fiber. Due to the fact that the Brillouin gain spectrum is order of magnitude wider than the separation delta N that we used, 3 acoustic tones were generated in the nonlinear mixing process. One at the Brillouin frequency and the other 2 at the Brillouin frequency plus delta N and minus delta N. To derive the model for the interaction, we first performed a series of standard approximations. We used the slowly varying envelope approximation. We assumed steady state conditions, which allowed us to neglect the temporal derivatives. We assume short interaction lengths, which allowed us to neglect the linear losses, which is certainly suitable for optical fibers. We also assumed undepleted pumps, which linearizes our system, as we already discussed. And we also assumed that the acoustic waves adiabatically follow the spatial evolution of the pump probe bit node. This effectively means that the photons are strongly spatially damped compared to the lengths over which the optical amplitude changes appreciably. And we performed the rotating wave transformation and assumed that the separation delta n is smaller than the Brillouin line width, as we already mentioned. Following these approximations, the coupled nonlinear wave equations reduced to the following Schrödinger-like equation for the two probe tones, A1 and A2, where H naught is the anti-PT symmetric Hamiltonian of the system, which depends on the separation delta n and the pump's power. Let's take a brief look at the very simplified and also at a slightly less simplified schematic illustration of the experimental setup. Important to know that all optical signals used in the system were drawn from a single narrowband laser source in the telecom wavelength range. The magnitude and phases of the two input probe tones, as well as the separation delta n, were controlled independently by an arbitrary waveform generator. The separation between the pump tones was controlled by another RF generator, and their intensity was controlled by our high-power erbium-doped fiber amplifier. The fiber under test was a 10-meter-long, commercially available single-mode fiber. Following the Brillouin-enhanced 4V mixing process, the output probe waves were detected by a coherent photoreceiver, recovering their amplitudes and phases. And finally, the transfer matrix was estimated through n input states for different settings of the system parameters. So this is how the actual experimental setup looks like. That's the one on the background here as well. I guess this is what happens when you combine benchtop experiment guidelines with the possibility of using off-the-shelf components. You end up taking all components in the lab and trying to fit them on a test bench. While the state preparation and detection might look a bit complicated, the effect actually takes place in the spool of fiber you see over here. Apart from carefully tuning the working point of each modulator and the power levels at each connector in the setup, it is important to synchronize the phases of all RF generators in the system and the oscilloscope trigger. Otherwise, you will not be able to properly measure the bit nodes of interest and their relative phases. Here you see an example how it looks on the scope when it's not synchronized, when you partially synchronize the system, and when you fully synchronize the system. So yeah, this is a major item. So here are the results, as you can see them on the right. On the left, you can see the analytical derivation of the eigenvalues of the system Hamiltonian. The experimentally retrieved eigenvalue spectrum agrees well with theory, and we are able to observe a phase transition between anti-PT symmetric and broken symmetry regime with large precision. We also observe the exceptional point singularity in agreement with the model. Away from the exception point, the separation between the eigenvalues depends linearly on delta n as expected. However, near the exception point, we observe a square root dependence on small changes in delta n in agreement with our analytical predictions. This enhanced sensitivity, however, is not very useful for environmental sensing purposes. It simply sets the limit on system stability. The uncertainty in measurements of the system eigenvalues is in the order of 10 to the minus 3 inverse meter, which is 10 of orders of magnitude smaller than the optical wave number. Now I will show you that we also observed enhanced spectral response to changes in the Brillouin frequency shift, which is the single most important mechanism in distributed fiber sensing of environmental parameters. Let's assume that we detune our system from the Brillouin resonance by some delta Ni Brillouin. The modified Hamiltonian can now be approximated in terms of a first-order perturbation correction as follows. We define the perturbation delta Brillouin as the detuning from Brillouin resonance only normalized by the Brillouin line widths. The eigenvalues of the modified Hamiltonian are now written as follows. And what is remarkable is that if we tune the system to the exceptional point of the unperturbed Hamiltonian, we expect to see a square root dependence of the splitting also on the deviations from the Brillouin frequency shift. This is indeed what we observe experimentally when we characterize the real eigenvalue spectrum as a function of the Brillouin detuning. We performed the experiment 3 times below the exceptional point, as close as possible to exceptional point, and above the exceptional point. The splitting of the eigenvalues is the largest when the system is adjusted to the exceptional point. This is seen more clearly here on the log scale, with splitting measurements as a function of the Brillouin detuning at the exceptional point, marked here in red, having the smallest logarithmic slope. Potentially, this enhanced response can serve for environmental sensing. However, there remain some open questions with respect to the dynamic range and precision of the sensing mechanism before we can claim superiority over other available Brillouin sensing techniques. I want also to point out that the uncertainty in the estimate of the Brillouin frequency shift in our measurements was 50 kilohertz, which is the equivalent of 0.05 degrees Kelvin. I could not have expected any better stability in the uncontrolled environment of our laboratory. For completeness' sake, I ought to say that we initially disregarded the cascaded buildup of additional sidebands in our system. The Brillouin gain in our experiment was on the order of 5-6 dB, which explains these sidebands we observe here on the right, even beyond the first order. Due to this approximation, we failed to accurately estimate the average Brillouin gain, as can be seen in this discrepancy between the model and measurements of the imaginary part of the eigenvalue spectrum. The symmetry with respect to the Brillouin detuning, which you also see here, could not be predicted using our two-level Hamiltonian. Nonetheless, the key predictions of the simplified two-level model, such as singular response to small-scale variations and topological feature, hold very well. Picking up on where we left off with regards to sensing, the following analysis of the measured Brillouin gain spectra of the two probe tones may appeal better to the Brillouin sensing community than the square root dependence of the splitting of eigenvalues that we showed before. So here we projected the system outputs onto their corresponding eigen-mode basis. We did it at 3 delta Ni points, above, at, and below the exceptional point as before. The x-axis here represents the phase difference between the two input tones, and y-axis is the Brillouin detuning. And the experimental observation also agree well with our model. So what we see here is a spectral narrowing of the Brillouin gain as we approach the exceptional point from above, reducing to some 4,100 kilohertz in the vicinity of the exceptional point, and a discontinuity in the projected spectrum as we cross the exceptional point. As we already mentioned, the applicability of these features to sensing is still under study. One thing that seems more certain at this point, though, is that there are ways to make our system more robust using additional non-Hermitian tools that were developed over the years. If we look at the Riemann surfaces of our system, we can immediately identify that in order to get enhanced sensitivity along the Brillouin detuning axis, we need to tune our system to the exceptional point along the orthogonal axis. the accuracy along this axis is compromised by different detrimental cross sensitivities in our system, such as pump power instability, residual imbalance between the two pump tones, polarization variations affecting the Brillouin gain and coupling strengths, cascaded buildup of additional sidebands that we saw above, etc. In this context, I want to introduce to you the notion of exceptional surface. Here, the authors of this paper is to introduce a unidirectional coupling between the degenerate counter-propagating modes of this micro-resonator by placing a partially reflecting mirror in the right arm of this bus waveguide. This two-mode non-Hermitian system is robust against fabrication errors and exhibits a degenerate spectrum irrespective of the exact parameters of the system. When a perturbation in the form of a scatterer placed in the evanescent field of the resonator is introduced, which symmetrically couples the two counter-propagating modes, we can observe a resonance splitting with a square root dependence similar to the case of an isolated exceptional point, but in a very robust manner. These principles can be potentially applied to our system in the future as well. Lastly, I want to show you another useful feature of non-Hermitian systems, which is the asymmetric mode switching when performing an adiabatic loop in the parameter space around the exceptional point. As you can see here on the right, the Riemann surfaces of our system exhibit a branch point topological structure around the exceptional point. The real eigenvalues are continuous and symmetric, while the imaginary part features a discontinuity in the broken PT phase. Therefore, for the eigenvalues to continuously change across this discontinuity line, they have to switch their values. In our two-level system, we expect one swap of the eigenvalues for one turn around the exception point. These are the experimental results. Here, we tune the frequency separation delta n and the pump probe detuning from Brillouin resonance. And for each such combination, we measure the eigenmodes in a stationary manner. Therefore, we could only assume that swapping will take place when we tune the parameters under a single excitation, but we did not directly observe it. If we were to continuously change the parameters during the probe's propagation, we will need to pulse it. We will also have to tailor the pump power and pump probe detuning using an arbitrary waveform generator. While this is in principle doable, to execute an adiabatic loop in the parameter space, we will need a much longer fiber, which is challenging in terms of maintaining the polarization, avoiding cascaded buildup of additional sidebands, and many other problems. Therefore, it offers no practical advantage to build such a system in the fiber. It makes much more sense to do it on a chip. We can harness the advancements in Brillouin-active waveguides to precisely control the acoustic dispersion and dissipation along the waveguide through structural modifications. We also expect that given the strength of the optomechanical effect in these waveguides, we will not need more than a few centimeters to achieve high switching efficiency. We expect that such a design will possess the following features. First of all, it will be optically transparent when the Brillouin pumps are turned off. It will be non-reciprocal by design because of the phase matching directionality, and it will be dynamically reconfigurable and support separation between the spectral channels of up to hundreds of gigahertz. Here you see the simulation results. You can see that for a counter clockwise control loop, above a certain length, the initial state adiabatically follows the system eigenstate. And for one turn around the exceptional point, we can observe an almost complete swapping. However, for a clockwise control loop, we end up in the same state as we started. This happens because the system jumps to the less damped mode at a certain point along the loop, which is also characteristic of these non-Hermitian systems. This effect is known as the asymmetric breakdown of adiabaticity. All in all, this leaves our system with a handedness-dependent energy exchange property, which was what we wanted. So to summarize, we have demonstrated the principle of non-Hermitian physics in a 10-meter strand of standard single-mode fiber. Our setup allowed for a precise and flexible control over gain and coupling and other relevant parameters. We experimentally showed an enhanced response to small-scale perturbations in the Brillouin frequency, which holds great potential for fiber sensing, pending the studies of the system stability and precision. We also have demonstrated the potential use of this method in Brillouin-active waveguides to realize asymmetric mode switching. And I think that the main take-home message of this work is that you can dynamically control the effective Hamiltonian of coupled optical and acoustic systems using optomechanical interactions, which is of great interest for basic research and a broad range of applications. Finally, I want to thank Andrea and Avi for this exceptional collaboration and all the wonderful people which I had the privilege to work with during my postdoc training. And I want to thank you for your attention. And I'll be happy to take questions if there are any.
Thank you very much, Arik, for the presentation. And we have time for questions. So again, if you have any, please indicate through the chat box and I will address you. And since I do not see one yet, let me, oh, there is one. Excellent. Birgit, please.
Yeah, so one question. So you said that it's probably better to take a shorter device. Is this only the polarization that is difficult for you in that case, or also other things?
Yeah, well, in order to do it adiabatically for a given pump power and optomechanical coupling strengths, you basically depend on one parameter. You depend on the loop length. So the longer you make it, the more adiabatic it is. So given the limited power, although it's not a very low power, we pumped almost 30 dBm into the fiber, but in the fiber, the interaction strength, the optomechanical interaction strength is comparatively weak. If you use a Brillouin-active waveguide, which has many orders of magnitude stronger optomechanical coupling, this is basically the ratio by which you can decrease your length. So if you need, let's say, tens of hundreds of meters in order to do it in a fiber, you can settle for a few centimeters of Brillouin-active waveguide to gain the same effect.
Okay.
So of course, maintaining polarization and all this cascaded buildup is something that you want to avoid, but you also don't want to build such a mode switcher in 100 meters of fiber. It's not very useful to do that way.
And when you say cascading, so this is anyway going like in two different directions, right? Or what do you mean with cascading, maybe?
No. You mean direction in terms of the frequency direction?
Well, the Stokes and then the next Stokes and then the next Stokes, they always
I understand. I think if I understand the question correctly, basically the reason for this cascading in our system is actually due to the fact that the separation between the pump and probe tones is much smaller than the Brillouin alignments, or much smaller than the gain spectrum.
Okay.
Therefore, you create 3 acoustic tones in the system, and therefore, while you don't have any optical energy in the sidebands when you start, it spontaneously builds up from those acoustic waves that you generate in a stimulated manner. Therefore, the more you propagate, the more energy you build up in these sidebands.
Okay.
Therefore, in our system, it was barely enough in order to stay within the framework of this two-level Hamiltonian. But obviously, if we would have used the longer fiber, this approximation wouldn't have held. Also, if you carry over this principle to an integrated chip, and now you can not only use shorter lengths, but you can also increase the separation of the tones way beyond the Brillouin line width. In this case, you won't have any cascading effect.
Okay, thank you.
Are there any further questions from the audience? If not, Arik, I would like to have one of my own. You discussed the potential for sensors due to the large response of the eigenvalues to small perturbations, and this was measured very clearly. And you also related to the certain controversy or dilemma that is surrounding this. Does this really signify an improved sensitivity? And this has to do with what happens to the noise. So what is the latest on that? Do we see enhancement of the noise close to these exceptional points or not? And is there a true benefit to be had in an actual sensor?
Okay, so this is a question of opinion and professional opinion, and not actually discussing actual results. But yeah, well, it's an excellent question because I actually have a slide on that. But it's not a published result, right? It's just what actually you see here is that if you just take the detection noise, right? Just take the additive detection noise, and simply use the same projections that we used for the measured signals, what you actually see here is the same effect of squeezing and same effect of this discontinuity also in the noise spectrum. Okay, so effectively there is no straightforward improvement in the signal to noise ratio as far as let's say the additive noise is concerned. Nevertheless, I think that these systems offer also a great potential in terms of not only increasing the raw precision of the sensing mechanism, but rather finding new handles on how, for example, to dismiss different cross sensitivities in the system. For example, this notion of exceptional surface, which also catching a lot of attention in recent years. So, and by the way, this is what, although strictly speaking, this is not a passive system, but let's assume that we refer to a linear system, a passive system. In active and non-linear system, this dynamics is more involved and more complex, and therefore, while for the case of maybe standard additive noise, this may not be some great news, but in other settings and in other systems, this physics may be very useful. For example, if you use, if you have, let's say, long fibers, you have all types of accumulated non-linear effects when you use these fibers for sensing, and therefore I think that these principles can be very useful in order to control the interaction and extract the relevant features out of it. And this is not very short answer to a short question.
Okay, so I think it is time for us to move on to the next presentation. So let us all thank Arik again.
Thank you very much
For the great talk.